Hey everyone, welcome back to another explainer. Today, we are unpacking something absolutely mind-bending. It's a tool set called Bitwise, and it completely reimagines how we compress, store, and transmit information. Seriously, if you've ever felt like our modern data infrastructure is just bloated, slow, or constantly hitting physical limits, what we're about to explore is going to radically shift your perspective.
Okay, think about this premise for a second. For decades, we've treated digital files like linear, flat strings of bytes, just a long, endless line of ones and zeros. But Bitwise asks a totally fascinating question. What if data is actually a physical, multidimensional object, an object that can literally be folded, knotted, and stacked? Instead of just reading a file left to right, what if we examine its topological structure?
To really wrap our heads around this unified topological framework, we're going to break this explainer into 5 key areas. We'll start with the geometry of data, move into folding the human genome, then shrinking human speech, streaming dimensions on the wire, and finally, the unbreakable Lacey cipher.
All right, kicking things off with part 1, the geometry of data, moving from flat files to folded shapes. So, let's talk about this concept called syzygy. In the Bitwise engine, syzygy is essentially topological folding. It's like the data makes what's known as a faith investment. It actually inflates and dilates into higher dimensions, explicitly looking for historical, repeating structures. And when it finds those structural loops, which are called Readmeister slides, it just collapses them. It treats these incredibly complex, repeating knots as a single, constant object, which massively compresses the data. You aren't just compressing characters anymore, you are literally collapsing geometry.
Now you might be wondering, what happens if you try this on perfectly random data? Like raw sensor noise? Well, you hit what is poetically termed the hope gap. This is a mathematical proof of pure entropy. The data dilates into a multidimensional space, hoping to find a loop, but because that data has zero history and no repeating ancestry, that dilated space remains completely empty. You essentially paid the spatial rent up front for a loop that never closed, so the file actually gets bigger. It's kind of a beautifully tragic way to physically prove that a dataset contains pure entropy. Moving right along to part 2, folding the human genome and how we shrink DNA using 54-dimensional math.
So, standard flat 1D packing, it maps 4 DNA bases per byte, which gives you a very predictable 4 times compression. But 3Z syzygy just totally shatters that limit. Because DNA is absolutely packed with evolutionary repeats, syzygy is able to fold those topological loops. On repeating sequences, like poly-A for instance, it achieves up to 333 times compression. It shrinks repetitive DNA down to microscopic sizes just by acknowledging its structure.
And Bitwise doesn't just stop at 3 dimensions. No, it stacks up to 54 parallel worlds of biological annotations directly on top of a single DNA sequence. Dimension 0 is your primary base. Then on top of that, you stack epigenetics, conservation data across species, transcription factor, accessibility, and complex RNA topology. The whole shebang weaves together into a massive 54-dimension multiomics file.
Now, I know exactly what you're thinking. Wouldn't a 54-dimensional file be impossibly massive? Well, actually, no. And it's thanks to something affectionately called the squirrel cheek effect. Because layers like epigenetics are incredibly sparse, they only sample every 200 base pairs or so, they gracefully hide, kind of like acorns, right in the unused topological gaps of the denser data layers. The structure dilates just enough to tuck that data away. This lets researchers add massive amounts of biological intelligence with barely any penalty to the overall file size.
Let's shift gears to part 3, shrinking human speech with the Pneuma Voice FLAC codec.
We all know audio files like waves are just notoriously huge, largely because they record raw, flat waveforms. Well, the Pneuma Voice FLAC codec completely stops treating audio like a flat wave. Instead, it slices human speech into 3 distinct geometric tiers inside a single wire packet. Tier 1 is just the raw phonemes, the actual linguistic intent at an incredibly tiny 54 bits per second. Tier 2 adds prosody, which is all the emotional intonation, and Tier 3 is the lossless acoustic residual. The beauty here is the system only downloads the specific tiers it actually needs.
And the results are wild. If you just extract that first phoneme layer, it turns out to be an incredible text compressor all on its own. When benchmarked on a 200 kilobyte English prose file, that phoneme layer shrinks voice transcripts down to just 2.44 bits per character. That matches the theoretical entropy floor of heavy-duty tools like Brotli. You are transmitting voice, but mathematically speaking, it's as lightweight as hypercompressed text.
So what is the big takeaway here? By stripping away that flat audio waveform and only transmitting the multidimensional linguistic intent, we get browser-native, lossless voice streaming at under 100 bits per second. That's literally 4,700 times smaller than uncompressed audio. It natively runs via W3C gzip in all modern browsers without even needing WebAssembly. And crucially, it allows large language models to ingest real-time speech context instantly instead of forcing them to process massive, clunky WAV files.
All right, part 4, streaming dimensions on the wire with edge-native, cot chain, and flow frames.
With traditional codecs, your system is compute-bound. Your hard drive is basically just sitting there twiddling its thumbs while your CPU grinds away at the encoding process. But Bitwise completely flips the script. Because its format packs and frames data in a single pass without any serialization boundaries, the Bitwise encoder is entirely I/O-bound. It structures data at a staggering 16 gigabytes per second. It is actually faster than modern solid-state NVMe Gen 4 hard drives can write. The disk literally cannot keep up with the math.
To put that kind of mind-boggling throughput into perspective, and this is just crazy, let's look at Notchain, which is Bitwise's edge-native blockchain. This system can stream encrypted 90-megabyte high-definition video directly from its raw chain data at 191 times faster than real-time.
And Notchain is nothing like the blockchains we're used to. It's a 54-dimensional columnar helix running on edge networks like Cloudflare Workers. Here's the kicker. It uses proof-of-not consensus instead of power-hungry mining or GPUs. It stores things like 20 complex cancer genes purely as topological state hashes, operating these blazing fast, multi-dimensional data manifolds for virtually zero cloud cost.
Finally, we arrive at Part 5, the unbreakable Lacey cipher and thermodynamic encryption proofs.
So how do you secure all of this? Well, the Lacey cipher operates inherently on the geometry of the data itself. It scrambles those 54 dimensions strictly in place, which means it adds absolutely 0 bytes of storage overhead. It's also steganographic, meaning to anyone on the outside, the ciphertext just looks like a perfectly valid, completely harmless data stream. Plus, through UCAN dimension scoped access delegation, you can assign permissions so precisely that a user might see just the DNA layer, while the other 53 layers remain completely scrambled noise to them.
And the security level is just staggering. Backed by formal mathematical proofs mapped in Lean 4, this rotating cipher boasts a key space of 2 to the power of 2,347. Okay, but what does a number that huge actually mean for us in physical reality? We are talking about a literal thermodynamic impossibility. Even if you could magically convert the entire mass and energy of our observable universe into one giant supercomputer, it would still only yield about 10 to the 90th power operations. The gap to crack the Lacey cipher exceeds 10 to the 600th power universes. It proves its absolute security on a physical thermodynamic level. Which actually brings up one of my favorite quotes from the documentation, one that perfectly captures the whole Bitwise philosophy. A good knot is a reusable, auditable container for complexity. A bad knot is trapped tension. That really hits the nail on the head, doesn't it? By embracing the complex geometry of information rather than trying to constantly hammer it flat, we create elegant, auditable structures instead of forcing chaos into inefficient files.
I want to leave you with one final thought to chew on. Today, we saw how multidimensional folding revolutionizes DNA mapping, crushes audio files to sub-100 bits per second, and creates thermodynamically unbreakable edge networks. Once we truly accept that data has physical dimensions, what other massive technological bottlenecks are out there, just waiting to be instantly solved? Thanks for joining me for this explainer, and keep questioning the shape of your data.